Hello and welcome back to Math with Mrs. Becker. Today in College Algebra, we are going to finish up section 3.1, which looks at exponential functions. Today, we get to focus on the base of e. For many applications, the convenient choice for a base is the irrational number e. Now remember what irrational means is that it continues forever and ever. It has no end, and there is no pattern to it. So if you round the first few values for e, you get 2.718281828. Okay, now notice it does appear to have a lot of 8s, but I can assure you that there are no repeating values within the base of e. This number is called the natural base. The function f of x e to the power of x is called the natural exponential function. It is an exponential function because your variable is the exponent. E is not a variable. E is a number that is approximately 2.718281828. Okay, so that's the hard part, is lots of times when you look at E, you're like, oh, that's a letter. But E is actually a number. It's kind of like pi. Pi is a number. It's 3.14159, and you keep on going, right? It's the same idea. When you graph e to the power of x, because it is an exponential function, it has the same characteristics as the graphs that we looked at in the first part of this section. Okay, the things like it's continuous, so you can sketch that curve without ever picking up your pencil. It is a curve-shaped graph. You have a horizontal asymptote going to either the right or the left. It is going to touch the y-axis at one location. So all of those properties and characteristics that we looked at in the beginning of the section hold true when our base is an e. Again, one of the key skills is just to make sure that you're comfortable using a calculator as we're entering these things. Your calculator does have e. If you are using the same calculator that we look at in the classroom, underneath the second key, if I go down 2, okay, so that's your natural log, it's an ln. Notice e is above that. So in order to get that, you have to hit the second key first, then ln. And one thing you'll notice right away is that it's e to the power of. E is always a base, okay? So no matter what, when you type in an e, I can't just do this. It's going to be an error because you have to give e a value for an exponent, okay? So let's go ahead and use this. They're telling us we have e to the power of x. We want x to be -2. So I'd have e to the power of -2. Now notice it opened a parenthesis. So one thing to kind of get in a habit of, if you have an open parenthesis, you always want to close it at the end. So this would be the base of e to the exponent of -2. Let's round it to the 100th, meaning I'm rounding to 2 places. I look at the third value, that is a 5, so I would bump that up to a 4, so it's approximately 0.14. Okay, again, if I want e to the 0.25, second ln. Okay, so I have e to the power of what? 0.25, close it, round it to the 100th, 1.28, because the 4 is not enough to bump that. I'm rounding, so I'm saying that it's approximately 1.28. If I said equals, what that means is that I need to include every single value. Well, that's impossible here because this is an irrational number. After the 7, there are more numbers. So we are saying that it's approximately 1.28. Last one, second ln. We get e on the calculator, e to the power of what? -0.4, close the parentheses, round to the 100th, and I have 0.67. So approximately 0.67. So that's the first skill that they really want you to know when you start working with the base of e. Make sure that you are comfortable putting e into your calculator as a base, okay? Just to kind of give you a visual for those characteristics, showing you that yes, it's still a curve-shaped graph. It's still going to cross the y-axis once. You're still going to have a horizontal asymptote. All of those different things. We are going to go ahead and graph a couple exponential functions that contain e by creating an xy table. So again, that's more practice entering into the calculator. We're going from -3 to +3. So -3, -2, -1, 0, 1, 2, 3. Now, when I enter this, it's a 2, base of e, so second ln gives us a base of e, to the power of what? Well, I have 0.24 times whatever x is, and x I'm taking right from the table. So I'm going to go ahead and put that value in parentheses as well. So -3, I have 1, 2 parentheses open. So you need to close it. Where you have an open parenthesis, you need to close. So in this case, it is okay. You're going to close the parenthesis to show that you're multiplying by -3. You're going to close the first parenthesis, indicating that that's where you have your exponent. Go ahead, hit enter. If I round to the hundredth still, 0.97. Now the cool thing, because I did put my -3 in parentheses, it's easy to find that. I just go back and look in the second set of parentheses. I change -3 to -2, and I have 1.24. Again, I can just up arrow. I can easily find that x value because it's in parentheses. Change the -2 to a -1. I have 1.57. Up arrow, I want to go to 0, delete the negative, change 1 to a 0. I get a 2. Now we're going to go ahead, change 0 to a 1, 2.54. And I change the 1 to a 2, 3.23. And last but not least, I almost forgot about that one. Let's go ahead and put in a 3. It's 4.11. So again, this is practice. How do you put something like this in a calculator? Now when we graph it, we will see those exponential graph characteristics. If I go to the left 3, I go up almost 1 unit. Left 2 up 1 1/4. Left 1 up 1 1/2. Ooh, 0, we jumped up to 2. 1, we're at 2 1/2. 2, we're up 1, 2, 3, and a little bit more. Go to the right, 1, 2, 3, I'm up 1, 2, 3, 4, and a little bit. So you can see that, yes, it's curving. It's not that steep of a curve. It's an exponential function, so we know it's going to have a horizontal asymptote. So there we go, continuous curve, one horizontal asymptote, crosses the y-axis at one location. Let's do one more just to make sure we've got this, okay? This time we are graphing 1/2 e to the -0.58 times x by creating an xy table that we are going to go from -3 all the way to +3 again. So -3, -2, -1, 0, 1, 2, 3. Now 1/2, if you prefer, you can use the fraction key and put that in as a fraction, or as long as you remember that 1/2 has a decimal representation of 0.5, you could also go 0.5. They are equivalent to one another. So if you are more comfortable working with decimals than fractions, you can always go ahead and do that. So 1/2, if I put it in as 0.5, e, second ln to the power of -0.58 times, now I'm going to take all those values. So I start with -3. Again, notice I have 2 open parentheses, close it. If I round to the hundredth, I have 2.848. So this is 2.85. Up arrow. Go ahead and change this from a -3 to a -2. 1.59. Up arrow. Change the -2 to a -1. 0.89. Up arrow. This time I want that exponent after the -0.58 to be 0. So delete the negative, change the 1 to a 0, and I get 1/2. Go ahead. Isn't this nice to up arrow? If we could not do this, it took me a while to figure this out. I used to enter absolutely everything. So that's kind of the cool part. I'm learning as I'm teaching, and I'm trying to teach you guys the little tricks. Okay, so that's 0.28 up arrow. Don't go back and re-enter everything. That'd be a big waste of time. Change the 1 to a 2. 0.156 would round up to 0.16. And our last number, what happens when you change the 2 to a 3? Are you ready? 0.09. So practice with your calculator. Now go ahead, go to the left. 1, 2, 3, go up 1, 2.85, so almost to the 3. Left 2, up 1 1/2. Left 1, up 0.89. Zeros at 0.5. Oh, look at that, 0.28, 0.16, and that's basically on the line. So this time, again, curve-shaped graph, continuous, crossing the y-axis at one location. This would be a horizontal asymptote going to the right. And so that's the first, or actually, sorry, that's the second idea. First idea, practice putting things in your calculator. Second idea, XY tables to graph exponential functions that have a base of e. Now here's our applications. When in real life do I actually need how to know, hold on, let's try this again. When in real life do I actually need to know this information, okay? There are times, this is something that you will use if you ever invest money or even when you put money into a bank like a CD or a savings account, that sort of thing. There are formulas, they're called compound interest formulas, and they allow you to see what the balance would be after a certain amount of time, okay? So if you are looking at something where it's compounding per year, and it might be compounded annually, that means once per year, semi-annually, that means twice per year, quarterly, 4 times a year, monthly, 12 times a year. If you have an account that compounds daily, that would be 365 because they would be adding money to your account every single day. That's super sweet. When you have something like that, here's what the equation is. A is the amount in your the balance in your account, okay? So that's just the ending amount. P is called your principal. And not Mr. Church, okay? P is the principal, the amount of money that you bring to the bank, okay? So whether you're investing it into a CD, into a savings account, P is your initial investment. 1 represents 100% because you are going to get 100% of your money back. So it's 100% in decimal form. Plus R. R is your interest rate. That will be given to you as a percentage, so you will need to change it into decimal form. N. N is the number of times that the account is compounded per year. So if it's annually, N is a 1. If it's quarterly, N is a 4. T is the time in years, okay? If you ever have something that is continuously compounded, that means it's not like a set time. It's just continuously like money keeps getting rolled over into that account. That's when you use, you've probably heard of it as the PERT formula. It's the principal amount E. E is a number, it's not a variable. E to the power of your interest rate times the time in years. So let's go ahead and use those equations to calculate some money. A total of $9,000 is invested at an annual interest rate of 2.5%. It's compounded annually. That means N equals 1. Find the balance after 5 years. Okay, so let's go ahead. This one, it doesn't say continuous. The only time that you use E is if it's continuously. This is compounded annually, so N is a 1. Okay, a total, that's your principal, $9,000 is invested. Then parentheses, 1, because you will get 100% of your initial investment back, plus your percentage as a decimal, 2.5%. Remember to turn a percentage into a decimal. You take the decimal that's currently there, go to the left 2 times. If you have a loop, you need to add a 0. So it's 0.025 over N. N is the number of times that money is being added to your account. In this case, it's a 1. 1 times the number of years that you're keeping that money in the account, that's a 5. So I can go ahead and have 9,001 plus 0.025 divided by 1 is 0.025 to the power of 1 times 5 is 5. We can go ahead and enter that. And let's see how much money we would have. See, this is exciting stuff. 9,000 times 1 plus 0.025, close it, to the power of 5. And your investment, you go back 5 years later and you're like, yo, I want my money. It's $10,182.67. So that's cool. Now, sometimes in this textbook, if you're doing the suggested assignment, they will have you calculate 2 different things. The first thing is find your balance. That's what this is called. Your balance is your total amount of money. Then it might say how much interest did you make. Now, interest is the difference between how much money did you initially invest and how much money is in the account at the end. So if I wanted to know my interest, you would just go ahead and subtract the original 9,000. And in this particular case, you made $1,182.67 by investing that $9,000. Super cool. Way better than if you took $9,000 and like put it in an envelope in your freezer or something crazy. This is why it's important to invest your money, have the bank hold it. You make money on your money. Super cool stuff. Okay, well, let's go ahead and look at another one. Calculate the amount of money in an account if $3,000 was invested at an interest rate of 6% compounded daily. That means that N is 365 because there's 365 days in a year. And let's do this for a time of 1 year. Okay, so you're going to keep your money in the account for 1 year. You're like, okay, I have this extra $3,000. I'm okay investing it now, but you don't want to do like a long-term commitment thing. You're like, 1 year and then I want my money back. So let's see what would happen. Your principal amount, you invested $3,000. Open a parenthesis, 1 plus. Your interest rate as a decimal, 6% as a decimal is 0.06 over the number of times it's compounded. Here we have 365. Your exponent is the number of years times n. 1 times 365 is 365. Now again, a big part of these type of skills is knowing how to use your calculator. I can enter this in my calculator, but what has to happen is you have to put an extra set of parentheses around this fraction. Okay, so this is what it will look like. 3,000. You go ahead and put how much money did you invest. Open a parenthesis, the number 1, because you get 100% of that back. Plus, now I'm doing a division problem within parentheses. So I open a parenthesis, 0.06 divided by 365, close it. And again, I have to close it because remember, anytime you start a parenthesis, you need to close it. So I have 1 to close because I'm dividing and 1 to close after the initial set of parentheses. Then to the power of 365. So you go back at the end of the year and you're like, okay, I want my money back. You brought in 3,000. They're going to give you $3,185.49. And if you're thinking, well, that's not a lot of money, you still made almost $200, and that was in 1 year by just saying, okay, I can put this aside for now. So big picture, it's a pretty darn good deal. Okay, last one like this. A total of $12,000 is invested at an annual interest rate of 3%. Find the balance after 4 years if the interest is compounded for part A quarterly. So A, quarterly means N is 4. So the initial investment, the principal amount is $12,000. 1 plus your interest rate is 0.03 over the number of times it's compounded. Quarterly is 4. Your exponent is N times T. 4 times 4 is 16. Again, I can go ahead and enter that into my calculator at one time as long as I put an extra set of parentheses around that division portion. 12,000, open a parenthesis, 1 plus. Now here's my division. 0.03 divided by 4, close it. To the power of 16. And again, this is 16 because if I look back at the original problem or the original formula, it's N times T. N is the number of times it's compounded times the number of years. In our case, we're going quarterly, so that was a 4, and 4 years. So 4 times 4 is how I got my 16. Let's go ahead and hit enter. The amount of money that you would have after 4 years is $13,523.91. Remember, we're talking about money, so always round to the hundredth. Now part B, compounded continuously. As soon as it's continuously, that's the PERT formula. So the principal amount, $12,000. E is a number. Your interest rate as a decimal, 3% is 0.03, times the number of years, which is 4. So again, I can enter all this in the calculator. 12,000 second ln. So it's e to the power of 0.03 times 4. Close it. I have 2 parentheses open, 2 parentheses closed. Hit enter. The amount of money that you would have is $13,529.96. So if you are given a question that says, okay, these are your 2 options, which one would you take and why? Hopefully you would say, I would do continuously because you make more money. Granted, it's not a lot of money, but it's still more money. And if you get a choice, you definitely want to help yourself out. So in this case, you would want to invest that $12,000 into the continuous option. Okay. Here is something that you probably talk about in science. It's half-life. Let's look at this example. Let Y represent a mass in grams of radioactive strontium. The half-life of strontium is 29 years. So what that means is whatever amount you have, 29 years from now, it would be half of that amount. And then 29 years later, it would be half of that amount. So every 29 years, the amount that you have lessens, it gets cut in half, okay? The quantity of strontium present after T years is given by this formula. So this is the formula that we're working with. What is the initial mass? So initial means at the starting point. So T would be 0. So if I have 10 times 1/2, 0 over 29. Well, 0 divided by 29 is 0. If you're doing your order of operations, your exponent comes before you multiply. So exponent, well, anything to the power of 0 is a 1. 10 times 1 is 10. They told us that our mass is in grams. So what's happening here is we are starting with 10 grams of strontium. We keep that. We're going to watch it 80 years later. Okay, so maybe you started this when you were like 10. And now when you're 90, you're going to go back and check your strontium, right? So you started with 10. How much would you have left in 80 years? So T is how many years? T is 80. 10 times 1/2, 80 divided by 29. And again, as long as you're comfortable with this bad boy, you can do this. 10, open a parenthesis, 1/2. If you want to be a rebel and go 0.5, go for it. To the power of, I'm going to put this in parentheses because I want to make sure that the calculator knows that the exponent is 80 divided by 29. If you do not put the parentheses, what happens is you're giving the calculator a chance to maybe take the exponent to 80 and then divide the whole thing by 29. So it's really important to go ahead and say that it's 80 divided by 29 in parentheses because now your calculator knows that this whole thing is your exponent. Hit enter. Holy smokes, 1.4777 grams. So you had your 10 grams of strontium when you were 10 and you were like, yay. And then when you turned 90, you still had a little bit left. Granted, it's a little. You only have like about 1.5 grams. But the cool thing is there would still be some left 80 years later. Cool stuff. All right, last idea. Let's talk about some fruit flies. I hope you guys are having fun. I love this section. Okay, so again, we are studying fruit flies. The approximate number of fruit flies in an experimental population after T hours is given by this equation. Now, here's my question. Who mathematically takes time to study fruit flies enough to formulate an equation to estimate the amount of fruit flies there would be? Do you guys ever think of this kind of stuff? As I said it, I was like, oh, that was like somebody's job was to study fruit flies. All right, let's keep going. Find the initial number of fruit flies in the population. Well, initial means at the start. So T, which is representing hours, T would be 0 because it's where we are starting. So it's 20 e to the 0.03, T is 0. Okay, I'm going to go ahead and multiply those. So it's 20e to the 0.03 times 0. Anything times 0 is 0. Now, if you think of your order of operations, you do the exponent before you multiply. Well, exponent, anything to the power of 0 is 1. 20 times 1 is 20. So we are starting, we got 20 fruit flies hanging around the house, right? Then we want to know how many fruit flies are there going to be in 72 hours. So you're like, go fruit flies. And 72 hours we come back and we want to know how many there are. T is hours. So that means T is 72. So if I have 20 e to the power of 0.03 times 72, go ahead and calculate that. 20, second ln gets you the e. My exponent is 0.03 times 72, close it, because that keeps everything up in the exponent. We have 173.4, so we got like 173 fruit flies and a leg and a couple wings. So we'll say we have approximately 173. We'll just count the whole fruit flies. I don't want to worry about the halves and the extra body parts. So we're going to say about 173 fruit flies. And you guys, we just finished section 3.1. We are right on track with our scheduling. I'm proud of you. I hope you had fun today, and I'll talk to you next week. Bye.